have one other extremely important aspect of electrochemistry to delve into, and that's contrasting a voltaic cell. And we are experts by now at creating a voltaic cell. It's a cathode that draws electrons to it from an anode. But we want to contrast that with something called an electrolytic cell. These turn out to be very important, for example, for plating chromium onto metal, any kind of plating process that involves the infusion of metal into another metal of less value, and many silverware, forks, spoons, and so on have a very thin coating of silver on them, so that they appear to be pure silver, but they actually have a core of steel, and there are many, many examples of this. But we want to look at the contrast between a voltaic cell and an electrolytic cell. And of course, we're now very familiar with a copper 2+ voltaic cell, which uses zinc as the sacrificial lamb, creating zinc 2+ aqueous at the anode. So we have electrons flowing out of the anode and electrons flowing into the cathode, because copper 2+ has a greater affinity for electrons than zinc 2+. So we also know that oxidation occurs at the anode for a voltaic cell, reduction occurs at the cathode, and the overall reaction involves a process that is spontaneous when it's allowed to operate independently. So a spontaneous redox reaction releases energy, and we can, by virtue of those electrons flowing in the external circuit, do work, heat, cool buildings, light buildings, whatever we wish. But we also want to look at the chemistry of what happens when we apply a battery into the middle of this voltaic cell. That's what constitutes an electrolytic cell. We're going to take a battery and we're going to apply a voltage such that the positive pole of that battery is going to draw electrons out of, in this case, the copper solution, and it's going to drive electrons into the zinc solution. So this is the case where, while the copper 2+ cation is capable of stealing electrons from the zinc metal, we can apply a battery such that electrons flow in the opposite direction. Now the important thing here is to watch what happens, because in an electrolytic cell, the anode is positive. That is, all of a sudden the anode becomes positive, the cathode is negative, and delta G is greater than 0 because we've applied the battery, the external battery, to that chemical reaction. So, as is always the case, we always want to sketch out an electrochemical reaction. We want to understand how many electrons are involved, but we also always want to draw the Gibbs free energy surface over which that reaction takes place. So let's take a look at this. So now, all of a sudden, by joining that battery into the external circuit of the electrochemical cell, we've taken our copper zinc voltaic cell, and we know exactly how that operates. In the absence of any external voltage, delta G is less than 0 and electrons flow downhill. But as soon as we apply a voltage that's larger than the cell voltage, which, as we know for our copper zinc cell, is 1.1 volts, if we apply a larger voltage to that, those two Gibbs free energy surfaces couple together. So let's take the lead acid battery that we use to start gasoline automobiles. The overall reaction for that is converting lead oxide and sulfate into lead sulfate. That's the overall reaction. But the half reactions involve two steps. The lead oxide and the sulfate combine with two electrons to form lead sulfate plus water. And the other reaction is lead plus hydrogen sulfate anion forming lead sulfate, producing two electrons. So we can calculate immediately what the overall voltage of the lead-acid battery is. It's the reduction potential for the reduction half reaction, 1.7 volts, minus the reduction potential for the anode reaction. And that gives us 2 volts for that lead-acid battery. Now, we can combine those cells. So typically, if we want 12 volts, we take 6 cells and we multiply that by 2 volts per cell, and we have the typical 12-volt automobile battery. But let's just take one cell. Let's just take 2 volts. Now, because we have 2 volts, and because we have this crucial relationship that delta G is equal to minus the number of electrons times the Faraday constant times the cell voltage, we know that because we have 1.1 volts here, we have the proportional change in Gibbs free energy. But that's true also of the lead-acid battery. We've got 2.0 volts. So these two Gibbs free energy surfaces couple together so that the 2 volts dominates the 1.1 volts, and that drives the 2 electrons downhill in free energy, and it drives those electrons up the hill on the other side because the 2 volts overwhelms the 1.1 volts. So that means that we're now driving electrons in the direction controlled by the electrochemical reactions of the lead-acid battery.